That was a pretty awesome discussion. I hope you enjoyed it. Thanks, Charles, for moderating that. Don't forget to chat with the community in the discussion area. Continue that conversation going. And up next, I'm really excited to welcome Alan Feder, and he's the principal data scientist at Invesco. And I just had a really great conversation with him at the DSS break, too. And he uses data science, statistics, and machine learning to solve problems and build products throughout the whole company. And we just actually, the first talk of the day was Moody, and he talked about NLP applications and finance, and now Alan is going to continue the conversation in this field, explaining how NLP is really being used in finance to help professionals do their job a lot more efficiently and effectively in the whole field. So be sure to drop Alan some questions in the live discussion area, and I really look forward to this talk. Over to you, Alan. Thanks.
Hi, thank you for coming to hear me speak today at Data Science Salon. My name is Alan Feder, and I'm a principal data scientist at Invesco. I live outside Washington, D.C. with my wife and 2 children. I'm excited to talk to you today about natural language processing in finance, beyond the search for alpha. If you're not familiar with alpha is trying to find outperformance of a given security in the market. Whenever I tell people that I'm a data scientist at an investment company, people immediately think about using machine learning for stock picking and supervised learning model to predict future prices. Obviously, that's very common in the industry. Most finance companies are doing that. If you're interested in that, I'd like to strongly recommend the book Advances in Financial Machine Learning by Lopez de Prado. He does a really great job there. Of course, people are using natural language processing as well. Many of you remember last year's GameStop craziness, which led researchers to scrape data from Reddit to try to get ahead of the curve and find the next meme stock. And of course, you could look at tweets to try to predict which cryptocurrency will become popular soon, what Bitcoin is going to do tomorrow. But I actually get excited about other areas of machine learning as well. I get particularly excited to build and implement machine learning models that work to amplify the intelligence of our analysts and investment advisors and allow them to use their skills that they've developed over their careers to do their jobs more efficiently and effectively. Now, of course, the type of products that I'm going to be talking about later today can be used by people in lots of industries, not just finance. I happen to be most familiar with finance, so those are going to be the use cases that I mentioned. But for those of you who are in other industries, I'd like to challenge you to think creatively on how you can use similar methods and models. Now, this type of work and products have some really strong benefits. Really, just automating machine learning can actually sometimes lead to a type of uniformity. And at a company like Invesco, which is focused on meeting consumer and customer needs, having models that allow our employees to incorporate flexibility can be really useful. One interesting flip side about these machine learning models use cases is that because our models are not necessarily automated, they're being used by the business partners and by the employees in our company, they actually have to choose actively to utilize the machine learning outputs we give them. Meaning that we have to constantly be keeping their trust at all times. I actually find it to be a really fun challenge to think about how to make tools that these skilled professionals will find useful and have amazing outputs, but that they will trust and want to use. Before I discuss ways that you can use it, I want to give a bit of a background into natural language processing for those who might not be familiar. NLP is a subfield of artificial intelligence that's been worked on since the 1950s. And for most of NLP's development, it's actually very different from the stuff I'm going to talk about today from the connection to machine learning. Much of NLP was focused on areas like formalizing and programming linguistic and semantic rules that were going to be used for processing and understanding language, both spoken and written language. Now, this is difficult. It's very easy for you to listen to me and understand what I have to say if I'm doing a good job. And it's pretty easy for you to read and immediately understand words on a screen. But that doesn't come quite as naturally to our computers that, at their core, are processing zeros and ones. Machine learning builds probabilistic models using data to attempt to accomplish many of the goals of AI. Machine learning really became big in the 1980s. People have been using machine learning with NLP since machine learning has developed, but there's been a real revolution over the past decade where machine learning models, especially deep learning models, have reached new levels in performance and accuracy. But the core issue is that machine learning is fundamentally math. Some linear algebra, a bunch of calculus, definitely some probability and statistics, while language is based on letters, words, and phonemes. So how do machine learning and NLP make the connection? One of the ways they can do that is through word vectors, dense representations of the meaning of each word into a set of numbers. The set is usually around 50 and 768 numbers long. Around 9 years ago, Google released Word2Vec, which calculated word vectors by using a neural network. It did this by trying to use each word and trying to predict each word's neighbors. The idea behind this is that words that show up in similar contexts, meaning words that often have similar neighbor words, will likely have similar meanings to each other as well. You can see an example of a demo output in the middle of the screen here. Each column represents something about the meaning of the word, how verby it is, how feline it is, and that's one way to turn a word into numbers. Now, most of the time, these types of models don't actually output vectorization quite as interpretable as the demo is here. But that doesn't mean it's entirely a black box. One of the ways people like validating that the vectorization makes sense and captures real meaning behind the word is by using analogies. You can do arithmetic on the word vectors to show that man is to king as woman is to queen, or Paris is to France as Moscow is to Russia. But over the past 4 or 5 years, there's been another sea change in the machine learning NLP world into using transformer-based models, the most well-known of which are BERT and GPT-3. The technical details of these models are way beyond the scope of this talk, but some of their biggest changes are that the word vectors for each word are dependent on the context. So if I say that I'm feeling well today, and you say that you drew water from the well, BERT and GPT-3 would calculate the word well differently. This actually leads to a number of operational differences with the previous approaches. One of them is that with a Word2Vec type approach, your model can output a dictionary, a mapping table. So if you want to vectorize your sentences and start doing machine learning on them, you just need to map each word to its dictionary. However, in the transformer type approach, you can't have a simple dictionary because the representation of each word is calculated based on its context. So to get any predictions or even any features using these models, you need to run the entire transformer model every time. And there's a number of packages that actually make it quite easy to run these models on your own data. The one that I've used the most is the Transformers package by Hugging Face, which has incorporated tons of models into them. So how can we use some of these transformer-based models in finance? The first task that I want to discuss is text classification. At a basic level, this is kind of like an NLP version of logistic regression. It's about classifying a given sentence or paragraph among 2 or more groups. From the alpha side, this is what people are doing when they say that they're doing sentiment analysis, classifying a text as being positive or negative. In our context, we might want to use it for topic modeling. For example, maybe you're interested in ESG and you want to classify news articles about whether they're about an ESG topic or not. Or maybe you have a whole ton of presentations by industry experts and you want to find which ones talked about robotics. while you could go through each and every text in your database and manually label them for later, using a model is much more scalable. Similarly, you might want to look through portions of financial filings and try to predict which ones will lead to material risks over the next few months, and a fund manager might use that in making their decisions. Maybe you want to look at tweets and see which ones predicted high volume of trading, which might help the traders in your company. So practically, how do we do this? For this, we use transfer learning. Transfer learning is actually an idea that I had a lot of conceptual trouble with for a while. I grew up as a data scientist modeling tabular data sets, structured data, the type you maybe see often from an Excel table. If I were to say try to use Salesforce data to predict customer churn, I'd never just take somebody else's churn model off the shelf and run that on my internal data. Both, A, because it wouldn't work very well, and also B, because nobody open sources their data like that, their models like that. When I would run random forest models, scikit-learn would just provide me the framework, sort of almost a meta model, not the actual parameters. In a lot of areas of AI, like NLP and computer vision, it's actually quite different. Training deep transformer models are actually impossible for me or you. Even when Google trained BERT from scratch, it took them 3 days on their supercomputers. Luckily for us, they open source not only their model, but also their parameters, meaning the numerical interpretations of each word. To explain that for a moment, this is a diagram of a standard neural network. If you're not familiar with neural networks, you can think of them as stacked linear regressions on steroids, to quote a line from the Neptune AI blog. Each arrow represents one parameter, and each circle is predicting the value of circles in the following hidden layer, going on until it predicts the output. If the person who trained the model open sources the structure as well as the numerical value of each arrow, the weights, the parameters of the model, you can then run that on your data. And even if you want to tailor this model to your own situation, because you have a different context or you have a different goal, all you need to do is fine-tune the model. Theoretically, the first few layers of the neural network will probably be capturing some type of basic level of meaning, and each subsequent layer will be capturing a more sophisticated concept. In image processing, people talk about lower layers as capturing lines, later layers as capturing maybe features. If you're talking about animals, maybe a given eye or nose. In NLP, you can imagine something similar as well, basic levels of linguistics to more complex levels. When we fine tune a model, we keep all the arrows in the first few layers frozen, but then we let the neural network use our data to fit the parameters in the later layers. It even uses the values that are already there as a prior, so our data doesn't have to try quite as hard to get great results, but it still uses the entire BERT corpus for the most basic layers. And it's really easy to do. I can't talk publicly about what topic we were classifying, but at our company, we had great success with fine-tuning BERT. In this example, we had 1,300 or so training examples, approximately balanced between two classes. We first tried using TF-IDF combined with a penalized linear regression. Both of those I'm not going to get into now, but those are methods that have been used in NLP for a while and predate deep learning. We got an accuracy of approximately 80% and an AUC of 0.9. Not bad. We then tried taking BERT, just taking the features from the final layer, and also sticking a penalized linear regression on that. And we actually did worse than TF-IDF. However, when we fine-tuned BERT, our accuracy and AUC jumped. This fine-tuning took less than an hour, and the code itself was only 66 rows, most of which you can look at yourself in the original tutorial. So if you have some labeled data and you want to build a classification model, this should be totally feasible for you. But let's say you don't have labeled data and you can't or won't invest in labeling data. Don't worry, you still have a shot at success. Before I explain, I want to give a background to a sub-area of NLP, natural language inference, NLI. In NLI, you have two sentences, two statements, a premise and a hypothesis. The model tries to assess how likely the hypothesis is to arise out of the premise. In the example on the screen, if the premise is that there's a soccer game with multiple males playing, the hypothesis that some men are playing a sport seems to naturally arise out of the premise because soccer is a type of a sport. If the premise is that a man is inspecting a uniform and the hypothesis is that man is sleeping, that hypothesis must be wrong. You can't inspect a uniform if you're asleep. All this leads to something that has been called zero-shot learning, topic modeling without labels by repurposing a model originally developed for NLI. All it does is use the text that you want to classify as your premise, and then set the hypothesis as this text is about whatever topic you want. So in our example here, I took the first two paragraphs from a New York Times article about a hack of the Washington, D.C. Police Department, and I gave it 6 possible topics. And the model correctly predicted that the article is about cybersecurity, even though I didn't use a model that was trained on these specific topics or about topics at all. I could have chosen any topics that I wanted to try to find the classification. I was particularly glad to see that even though the article said that the victims had to pay in Bitcoin, the model didn't get tricked into thinking that the text was about blockchain. Even though the article said that the Houston Rockets were hacked, the model didn't think that the article was about sports. Additionally, although the defaults in the Hugging Face zero-shot learning model that I linked to here are about topic modeling, the original research paper actually suggests that you can use this approach for a number of different things. For example, you can get the emotions out of a text by changing the hypothesis to be this text expresses, and then letting it choose a bunch of emotions. Now, if you have labeled data, fine-tuning a transformer like I showed earlier will almost definitely lead to better results. But if you don't have enough to even fine-tune a model, this could work surprisingly well. You can also think about how to use the different hypothesis structures to find a situation that will fit you very well. Beyond classification, another NLP task you might want to do is calculate how similar two texts might be to each other. For example, you might be looking through lots of similar texts, maybe a bunch of news articles all about the same event, maybe a bunch of analysts writing about the same company, and you want to find which ones show something different, are more exceptional. Maybe you're trying to compare some risk factors from annual regulatory filings, and you want to see what's changed from this year to last year. Part of the problem with using word vectors here, where you might think, hey, let's take the word vectors that come out of it and concatenate them all together, is that the lengths of the text may be different. Even if one text is 350 words and the other one is 351 words, their direct mathematical comparisons won't work at all. That's why we need to create what are called sentence vectors or document vectors. These methods create one standard-sized vector for the entire text. There's a number of ways to do it. The simplest is just to take the element-wise average of the word vectors for each word in the sentence. If you're using static word vectors, I've put it into Spacey, and you can get a good sentence vector from there. And when I've used transformer models, I can just extract it and then do the averaging in NumPy or PyTorch. The main drawback of this method is that it's a bag of words approach, even if some of the underlying vectors are calculated in a non-bag of words way. One way around this is that if you're using a BERT type model, the first word vector is actually the vector of a dummy word. Every sentence is preceded by a token, just a word that basically says we're starting the sentence now. So you can take the vector from that sentence as a representation of the whole. If you Google around, you're going to see a lot of disagreements and arguments about when and whether you can do it. I've had a bunch of success. Moreover, you can actually directly calculate a document vector without utilizing the word vectors first. If you're using a transformer type approach, there's the sentence transformers package in Python. More details are available if you Google SBERT. It's actually a very clever way that they train their models, using actually some of the ideas from NLI that I mentioned earlier, trying to count two sentences as similar, relating to the idea of entailment in NLI. Even if you don't want to go through a transformer type fully deep learning approach, the GenSim package implements a doc2vec model, which actually trains using a approach very similar to word2vec, but adds a vector for each text. And then once you've calculated the word vector for every text, you can run it through a cosine similarity statistical model. Cosine similarity, basically a vector, obviously we use it as a set of numbers, but you could also imagine it as an arrow or a line in a n-dimensional space. And if you have two lines, you can just look at the angle in between them. Smaller angles mean a more similar to set of texts. The last method that I'm going to discuss today is text summarization. This is the process of automatically shrinking and summarizing texts to their most important portions. There are myriad ways in which this can be useful. Whether you're building it for a fund manager, someone in sales, someone in investor relations, everyone has too much to read and not enough time in which to read it. Summarization can be used to decide whether they need to get into the whole thing or whether they can just move on. Some sections of annual filing, such as the management discussion and analysis section, can be shrunk to a more manageable length. If there's a long news article about a company you're considering investing in, summarizing it can allow you to get a gist of the meaning of the article. You can even decide to summarize long emails from your boss if you don't have time to read them all. One way summarization can work is through a sequence-to-sequence model. This differs from our previous example because previously we were coming out with one numeric output, a probability score or a similarity score. Here, both our input and our output are natural language. We do this by pairing an encoder model, like BERT, to a decoder model. To oversimplify, let's just think of a reverse BERT. This decoder model takes what comes out of the encoder model and reconverts it back into text. Now, when doing text summarization, we put a limit on the output of the model so that the decoder model is forced to choose only the most important parts to rewrite. Funnily enough, one of the sequence-to-sequence models that is performed best on text summarization is not BERT, but BART. The biggest issue I've actually run into when doing text summarization is that the default models have a limit. Often you can only summarize texts that are less than 1,000 words. Very often we need to be summarizing texts that are significantly longer than that. The two ways around that are looking in a model hub and finding a model that has a higher limit. What I've actually found more useful is to basically break our texts into shorter segments, summarize each one, and then combine the summaries at the end. It's actually done really well and make sure you get summaries of every section. And it's actually really easy as well. I took the text of a different New York Times article about cybersecurity. This is just the headline and the subheadline. You can find the article itself if you want to read it. And I ran it through a summarization model. You can see here my code is really 3 lines using Hugging Face's pipeline. You can also see I defined the minimum and maximum lengths for the summary. If I needed something even shorter, I could have made that happen. And if I needed something to be somewhat less summarized, I could have ensured that that would happen as well. I actually think that this is a pretty clear summary, and it captures what was mentioned in the article pretty well. So just to summarize my own talk, I want to reiterate that NLP, including deep learning transformers, have lots of uses within the finance field, even beyond stock price performance. For those of you who are listening from other industries, I hope this talk also gave you ideas on how you can use these models, methods, and products to amplify the skills at your company of those who are already doing a great job. And you don't have to be a PhD in computer science to do this. The tooling has developed to a point where most data scientists, I think, can figure out, at least with a little bit of practice, how to code a basic inference model. The much harder part for a data scientist is to figure out which model to use, how to implement it, if the data, how to find a data set that works for training, how to find the type of premises and hypotheses that might work. That's where I think is the really hard part. But the actual coding part, I think most people can figure out how to use. I know that for many of the tasks, I gave a bunch of possibilities of how to do it. And online, if you look around online, there's way more possibilities than even that I mentioned. In general, the way I deal with this issue is to try a bunch and see what works best. You know, it's not necessary to eke out each and every basis point of performance in these models. Life is not a Kaggle competition. But you can very often eyeball the results and see if it makes sense. Look at the summaries. Does the summaries actually capture what we want? Look at a few examples of classification. Are we classifying things correctly? You can do this. And the last message that I'd like to give is pay attention to what's going on. Most of these methods weren't available 5 years ago, and some have even been developed over the past year or two. I'm sure that within the next few months and years, there's going to be some models that come out that make a bunch of the things that I mentioned today obsolete. So try to pay attention to what's going on in the developments in the NLP and ML world. You may be able to bring it back to your company. Thank you very much for coming to hear me talk today. If you have any questions, feel free to message me on LinkedIn or on Twitter. Here's the link to the slides if you want to look at it later on. Good luck on your NLP journey and at the rest of the Data Science Salon.